All right, good morning, ladies and gentlemen. You are not watching this on December 1st, but it's December 1st. Only 18 more days left until Christmas break. Woo! Didn't we just get back from break? Okay. Okay, so this is just review torque two-step. That's with the diving board that we talked about yesterday. So for rigid objects in equilibrium and two unknowns, we use the torque two-step, which is that system of equations.
System of equations with plural for equations.
Okay. So step one, you have to look at the translational motion, and translational being,
All points move parallel to each other.
and it's a non-accelerating system.
That's right.
In the x-axis, the net forces are 0, and the y-axis, the net forces are 0. So that means you can set stuff equal to each other. And then step two, you need to look at rotational. Rotational being like this sort of, or like that, right?
Yeah.
And when we talk about rotational, we use torques.
Yep.
And our net torques are equal to 0.
The torque in the clockwise is balanced out by the torque in the counterclockwise.
So
there is no
clockwise.
There's no angular acceleration, whatever the heck that is.
It's just chilling there.
That's right.
Okay, so whenever we do a torque two-step, we want to solve a step for one variable and insert it into the other step to solve for the other variable.
On the diving board thing, what we did is we solved the torques first, and then we got a value for that and plugged it into the translational, and it allowed us to solve the problem.
Okay. And then, so this is our problem that we did yesterday. A 530 Newton diver stands on a massless board. Thank God it's massless. What forces are exerted on the board? And what direction are the forces here? So if this is my diving board, if I'm going to hold this up right here, obviously the person is down, right? But if I was to let this go, it falls, right? So this is pushing up, and if I let this go, it goes up. So this is pushing down.
Yeah, everybody get that? And you can try that with a pencil or something.
Yeah, you can totally do it with a pencil. And when you're doing your torque two-step, you can either make this or this your axis of rotation. I tend to make it this one, but you can also do it with this one. They work the same.
And the idea is here, you've got the lever arms. That's 1.2 meters and then 1.4 meters, and you've got the one force, the force of the person, so you can solve for one torque. You can solve for the torque and find the force either on the end or in the middle, and then plug that into the translational.
Because this plus this has to equal this one, right?
That's right.
They're balancing each other. No acceleration.
It's a simple thing. It's a simple thing.
Yeah. Okay. Can you find the center of a meter stick with your eyes closed?
Yeah, what's going on? Why does this work? Watch your hands. Notice that only one hand moves at a time. And why is that? Well, it's because of friction, right? If one is sliding, there's less friction than the one that is not sliding.
Yeah.
So, and what's actually happening is there are two torques. You go out, put your hands apart again. There you go. And it can rotate around her right hand or her left hand. Yeah. Yeah.
Okay.
We won't go into the details of that because it gets really complicated really fast.
We're going to keep it simple. Actually, you know what? We were going to draw one thing, though. Separate from the, there was a question on the homework, actually, that was like this. And it talked about how there was two posts holding something up. And then there was the center of mass. Make this a little bit bigger, like this.
I don't think you want an arrow down on the right, do you?
I guess
the right, on the far right.
Oh, sorry, no. I wanted it like that. Okay, like that. Okay, and I'm actually gonna go to my next slide here. Center of gravity, the point on a rigid body where its weight acts when torque due to weight is being calculated. So, basically the center of mass is where all the weight is.
Effectively, it's as if all the weight were at that point.
Yeah. So if this was the center of mass right here, we could use our system of equations to figure this out.
Yeah.
Right? We could say that this was our force 1, this was our force 2. We could make this our axis of rotation. We know that torque 1 equals a torque 2. We can use force 1 and force 2 to find that, right?
Yeah.
Force 1, oh, actually, let me make this.
Show the lever arms
Yeah.
first.
Yeah, so our lever arm for force 1 is from here to here.
That's
So
L1.
that's going to be a little, okay? And our lever arm from here to here is going to be a lot bigger, right?
It's going to be big.
Lever 2, which means that this force has to be little, this force has to be bigger.
Yeah,
right?
that's like 10 times 2 is equal to 2 times 10.
Exactly. 10 times 2, 2 times 10, right?
That's right.
And
they balance.
And they balance, and this is what we're talking about when the net forces when the net torques are 0,
Yeah.
right?
Now, there's a picture in the book about center of gravity.
Oh my goodness, this is a great picture. Okay, take a look at this airplane, and what do you notice here about the front wheel?
It's up off the ground.
It's
That is
up-
not a good thing.
Yeah, this is no go. So what's supposed to happen is that the center of mass, essentially all the weight is acting like it's in this one spot.
You want it between the wheels.
Yeah, between the wheels. If it's not between the wheels, like here, and it's back here, what happens?
Put too much heavy stuff in the back of the airplane.
Mm-hmm.
And so what happens is the center of rotation is this right here, and you have a torque here and a torque here, and it ends up flopping back. And that's
no
a
good.
real thing. Somebody probably lost their job here. You're fired.
Don't be like that person. Okay, so your homework tonight is page 244, numbers 12 and 14.
Give them a shot and we'll talk about them in class.
Okay.